Okay, good morning, everybody. We can start this remote lecture. The class is empty. I'm the only one here with masks. You would report me to this campus security if this was last year. But now if I don't do it, you will report me. I'll let you think about how we behave. We're going to continue on classification problem. So we wanted to cover some background for machine learning course. These are really relevant machine learning problems that you will study seriously in a machine learning course, and part of it in the optimization course. So we had two sets of data points. We wanted to find a hyperplane that separates them in the space. That's called the separating hyperplane, or the machine learning jargon for it is it's a classifier. It classifies data into two sets. And it's a binary classifier. Later, you will learn that you can have a multi-class classifier. If it's more than two, it's a multi-class. If you have two classes, that's a binary classifier. Okay, so now the formulation we used was the easiest possible problem, because you see that data is separable. That means that we can already see that we can draw a line, and that will perfectly separate crosses from circles. But the reality most likely is not like that. You will have some overlapping part. For example, you will have some red circles on the other side and some blue crosses on the other side. And we're going to see what we can do to fix that problem. Now, if you have a data set like that, which I encourage you based on the new examples that I'll show you today, try the previous classifier. You will see that it does not work. It will fail, and it cannot find any valid numbers for the weights. And it will return nan, not a number, N-A-N. So if data is not separable, the previous formulation simply doesn't work. So there was that assumption there, but we ignore it just for the sake of building up from a simple example. So we talked about we have a hyperplane. There's a bias term, which is the distance from the hyperplane is the intercept. And we could stack them into a vector weight, and we have weight transpose times x that is augmented with 1 for the bias term, or you could say x transpose w. It's the same. So it's basically a sum over a weight times each element of our vector x. And that's our model. That's our function. That's called a linear model. And finally, the formulation we came up with was a quadratic program. We said that let's solve a norm minimization problem. Minimize the norm squared of the weights such that when we compute the distance from a hyperplane that we're looking for, W will give us that hyperplane, each class falls on the opposite side, on the side with its own group. That Y label times will control the sign. So this is really a sign distance. That's something that you probably early on in machine learning, they will talk about it. This is a sign distance because we don't take the absolute value. We don't care about just the distance. We want to know which side of the plane. Okay, so, and then we decided that we're going to pick a hard margin. That one was a hard distance from each side that we enforced to be as part of the problem formulation, which you can change it if you want to. Okay, so this hard margin is the reason it does not work if you have data with overlap. So can anybody think of any solution? What we can do to this hard margin to make it a little better? We don't want it to be, so now, right now, the classifier is really uptight. It gets irritated. If there's one point on the other side from the opposite class, it fails, it doesn't work. We want to relax it a little bit so it doesn't get that much irritated. It's okay. If there are some errors, still we want to solve the best, find the best plane we can. It doesn't have to be perfect. So if you have any idea, let me know in chat before I start writing our new problem. You can speak up too, if you want. Can't see the chat. Trippy, is there any message? Oh, chat is here.
Not yet. It says, do we just minimize the error?
Do we just minimize the error? Good question. We are not really minimizing the error because we want to find the minimum norm for our hyperplane such that the constraints are satisfied. We more care about satisfying the constraint and find the simplest model. Minimum norm corresponds to simplest model. So in that sense, we really want to modify the constraints. Let's think about the constraints, what we can do to them. Yeah, I think that's an important way of thinking about problem because we're after a minimal model because we do not know the actual value of the W. We're searching for that model function that gives us that. So here is an idea that we're going to do, which you hear it in an optimization course more formally. I start with our original problem. By the way, we call this soft, maybe this gives you an idea, soft margin classifier, as opposed to the previous case, which was hard margin classifier. So soft margin classifier, if we start with problem 1 was minimize 1/2 of norm squared of W such that constraints are satisfied. I am going to now, what I'm going to do is just an intuitive idea. You could come up with another idea. It's been a very successful idea in optimization. We're going to cut this model some slack. And then we're going to add some variables. It's called the slack variables, which is literally we're cutting some slack. Okay, don't go crazy if the constraint is not satisfied. Just tell me how much you're violating it. So we're going to minimize still. So we don't change the error per se. We say that just still find the minimum weight hyperplane such that I am going to use a crazy Greek letter. Brace yourself. This is called xi. In LaTeX, you can write xi. So now we're saying, and xi is zero or bigger than zero. So we're saying now, it's okay if you're not outside of those plus minus 1 margin. You can come inside, and then we're adding the slack variable. But instead of solving just for W, now, previously we said solve for W. I'm going to write it in red. This is very important. When you write an optimization, you should mention what variable you're solving for. Here, we are solving both for W and the slack variable. These are called slack variables. Okay, we have a new problem. Question. Is problem 2 still a QP? Is problem 2 still a QP? It's very important because, well, we have a limited knowledge. We know by now how to solve a QP. If it's different, we might not know how to solve it yet. Okay, any guess? You can say yes or no. I won't hold it against you if you guess randomly. Yes. So we got 2 yeses and 1 yes from me. We got 3 yeses. So it's a QP. Because, well, we didn't change much. The cost, the W norm is quadratic. The constraint still is a linear constraint. We just introduced a variable. Now we're going to go through a little crazier path to convert this into the stacked form, in the matrix form. But besides that, nothing has changed. This is still a linear constraint, just more variables. Okay, so now, this is the important part. I'm going to walk you through how to convert this. Which, again, I reiterate that your job will be how to write this problem, how to formulate it. Your job won't be writing the solver. You just use the solver. Okay, let's dive in. We are going to, oh, I forgot. We also need to minimize the norm of the slack variables. I totally missed that. That's also important. It's in the constraint. It's also in the, and we add a coefficient called lambda, or you can call it something else, to just adjust the ratio, the importance of the slack variables or weight. So this is very common in optimization. Now we have two terms. One is norm of the W, the other one is norm of the slack variable. Now in problems such as this, which is a quadratic or linear program, you can always convert it into, again, one variable. But important is that this is a multi-objective now, and that lambda is a trade-off. There's a concept in engineering, it's called Pareto optimal. Pareto optimal means it's always a trade-off. You have, for example, you have cost and you have performance. Now, you can go all the way and increase your performance to 99%, but then the cost is so high that it's just not viable. Or you can minimize the cost so much the performance is just makes the product useless. So you say, okay, I can't do that. I want to maximize performance, but I also want to minimize cost. How about I just combine them into a multi-objective problem, which is a weighted version of them, and find a middle point. Find the one that maximizes the performance while minimizes the cost, which is hard for us to guess, but computers are really good finding those middle points for us. So this notion. It's very intuitive. You can relate this notion of multi-objective to anything in life that you want, and you're gonna see it a lot. Okay, so I am going to write this as minimize lambda W transpose times W plus 1/2 C transpose times C. Okay, and what about the constraints? I am going to introduce some matrices here, which we will define it soon. Notice that I'm dropping the I because now I'm talking about vectors. Perhaps I should write it as this curly sign. All right, so here we have, remember, if we had X and W previously in an m-dimensional hyperplane, and if we had n data points, then our slack variable, because we have as many of them as the number of constraints, if we have n data points for the data set that we talked about it, then we're going to have an n vector of slack variables. What else? And phi, it's a regressor matrix that you did use it in project 2. I will define it soon. This is going to be, well, W is m by 1, and I have n constraints, so it's got to be n by m. Without knowing what is going to be inside it, I can guess it's going to be n by m. That's, I guide myself before writing it down. Okay, we got this nice vectorized form. I'm going to do one more try. Now I'm going to say minimize over C and W. I did violate the margin of the paper. How about We just stack all our variables and can I write it like this? Let's take a moment and appreciate what we see. I'm converting that multi-objective problem into, again, a single problem. And you could rename your stacked W and C to something else, Z or some other variable. Okay, I'm going to finish this and then see if you want me to explain any part of it. And for the constraint, I want to combine all my constraints. Remember, our solver was taking all at once, a giant matrix of constraints. So I'm going to write it as V is n by m. I'm going to have an identity matrix n by n. Then I'm going to have zero matrix n by m, which, by the way, these zeros are, you can guess that, well, I need n by m, and here I need m by n. Sometimes we drop it because you can guess it from the diagonal terms. So I'm not doing anything except writing my linear equations in matrix form. However, I am using a block form. That means each term is a matrix itself. So it's like a block version of what we used to do. So it's not going to change anything. But when you do in a block form, you think about vector matrix multiplication as you rearrange them. Okay, so I am going to write my vector of decision variables, and I ended up going outside of the paper. 1, I'm going to add infinity and negative infinity and 0 n. Now, this is just the vector of 1, 1, 1, n by 1. Similarly, this is just 0, 0, 0, n by 1. Same thing for the infinity. And I guess the rest should be clear. Now, this crazy matrix here is 2n by m plus n. Dimensional because, remember, if I have 3 weights for a line, and if I have 100 or 1,000 data points, let's say 100, now I am solving for 3 plus 100 variables, 103 variables. So it's a much, much harder problem to solve. We are not just looking for 3 weights, we are looking for 103 weights. So that's really high dimensional. It's not something that we can do by hand. And you will see that the solver is just doesn't care. You just pass your variables, and we're going to blow it up to 400 variables, still doesn't care. Now, I haven't tried an IllumiDisk on my laptop. On a normal laptop, you can solve it easily. computationally speaking. Okay, so yeah, if you are comfortable with this, I'm going to take you to the code. If you have a question here, let's talk about it first. Any part of it that maybe I moved too fast? A recap? Okay, so, oh, we didn't define phi yet. That's right. So there's another question is, how are you multiplying a 2 by 1 and 2 by 2 matrix in the first line? Let me understand it. Oh, you are absolutely right. This is transpose. Does it make sense now? Okay, good catch. We need a quadratic form. We can't. That's just syntax error because we couldn't multiply a vector like that by matrix. That is really good. So let's add phi. Phi is our regressor matrix, and it's nothing but the stacked version of our constraints. So we have minus negative y1 x1 transpose all the way to negative y1 xn transpose. Now, X is m-dimensional. X transpose will result in m columns for phi, and we have n data points, therefore this is n by m. And y, remember, is just plus 1 minus 1. And the negative sign here is because in the original problem, the constraint was saying that it must be greater than 1. Well, the way we want to enter it in the program, in the computer, it needs to be less than 1. So we add a negative sign to both sides. Okay, so which this should remind you of things you did in project 2, because now you immediately think that, well, if I have x like that, can I use polynomials? Can I use RBF? And that's exactly what we're going to do. But let's bear with me. We solve the linear form. That's how we're going to make it nonlinear, but still the function is linear. When you hear a linear model in machine learning, it's linear in weights. It's linear in W. The basis can be nonlinear. So as soon as you hear it's a linear model, when a machine learning guy is talking to you, you should think about, well, it's talking about the weights are linear. The basis can be nonlinear. It doesn't mean that it's actually plane. It can be a RBF, radial basis function, or some other polynomials as basis. So that's important to know. Okay, I'm going to take you to the code now. Well, let me upload So I uploaded my code in case you want to try it with me. I am going to use the soft margin SVM. I'll tell you why I call it SVM. You don't have to call it. But that's what people are going to call it in machine learning. Okay, so soft margin. I used my previous code, so I changed a little bit, but so you can do a lot of code reuse once you have the first basic version of it, which is always a good practice for coding. You start with a basic version, you figure out the pipeline, and then you make it more complicated from there. All right, hopefully it won't be very slow on Illumidesk. So you can see I'm writing my problem here. I wrote it for you here. So you have the typed LaTeX version. I do have the form that you can literally implement in the solver. And we have our regressor matrix. And I'm generating data, but this time in line 14 and line 19, I didn't think about it much. I just found some numbers that I find a data set that they violate the boundaries. You can play with it. But I'm letting them interfere, two classes. I don't want them to be fully separated because that's just too easy. Now try this data with the previous case when you don't have a slack variable. I did that, it fails. This is really slow. Which now that we're at this point, by the way, you might, if you like what we did in this course, you're hoping to continue, and I hope you continue, because this will have a great impact on your career, no matter what you do. Maybe it's a good time to start trying to do things locally on your own laptop. Now, I understand you might not have access to a good computer, but whenever you get your hand on a computer, or hopefully you can come on campus, try to run things locally, and that's a process to go through it. And feel free to ask us if you have questions about that. Piazza is a great place. You guys can help each other in that regard. Okay, this is going to take, I might try to run it locally. I should be able to run it on my computer. Since working. And I'm going to tell you one more thing while this is running. Now that you use Jupyter, Julia, a lot of these packages that we talk about, this classification, it is just like the solver. We did not implement the QP solver. Similarly, you should not implement this. I mean, you should, for practicing, understanding what's going on. Later, when you do a project, which is not specifically about implementing this particular, in a machine learning course, they might ask you to implement it. But any other place, you want to use a library. So these are all implemented. One example is scikit-learn. This is a great, massive library for machine learning, classification, regression, clustering. Probably everything that you want, you can find here. You can see SVM, nearest neighbor. So I encourage you to look at this and get familiar with Python, because Python is the language that right now is the #1 language people use in machine learning. Now, you can run Python in Julia. Julia is more fun to do linear algebra. It's more natural. But Python is older, so that's why people, maybe in the future they switch to Julia. But for now, Python is the #1 language. And you can run Python code in Julia and vice versa. So it's very compatible with Julia. So this can be your little project. Just look at this, try to install it, run some code, replicate some classification. There are lots of examples and demos, and if you just Google, you can find lots of it. And here is also there are a lot of it. So I encourage you to look at this. Just knowing how to use this library and do some classification and regression should give you a lot of new opportunities. Okay, so finally we got our packages loaded. Let's generate some data. All right, so now you can see that this is not too bad, but still the boundaries are, I'm going to try again. Oh, this is really bad. So you can see that there's a bunch of red dots, so all the way inside the blue region. Now that can happen because there are imperfections. In reality, data is not perfect. It's always noisy. You get outliers. Those are called outliers because they're not part of inliers. These are the correct ones. We know it because we generated the data. In reality, you don't know, which makes it extremely difficult. All right, let's, so you can see that I am defining my M here is 3, N is number of data points. I'm just literally implementing those block matrices here, which you should go through it and make sure you understand it. And it's great if you can discuss it in Piazza. We can have a discussion what's going on here. But the structure of it is the same as before. I did not change anything. I just changed these lines. That's it. Which is the beauty of using a solver. And later, when you use a machine learning library, I will search to see if there's a Julia version of machine learning library. There should be, but it's not going to be as mature as the Python version. But eventually, I think people will make it more stable. All right, now you see that we solved the problem, and we have results at x.x. We have, I think here, 103 variables. Now the first 3 ones are the weights, as before. Everything else here, these are the slack variables. One thing to know is that some of the slack variables are non-zero, like these two. Some of them, like this one, although you see it's like this, but it's effectively 0. These are very small number. Don't get deceived by the beginning that is a large number. It's really small. Okay, so you could just threshold this and say, okay, anything less than this, set it to 0 so I can see it clearly. Now, if a slack variable is 0, this means the constraint is inactive. It is not active, and that point in the data set, remember, for each point in the data set, we had a slack variable. So that means that slack variable is 0, the constraint is not active, and that point, surprisingly, has no effect on the solution. If the slack variable is not 0, remember, it must be positive. That was the constraint. Then we call that point a support vector. So that point is a support vector, and then that's where the name comes in. You hear support vector machine. support vector regression, support vector classification. This is the meaning of support. Because you find a set of points, a subset of points, usually it ends up being on the boundaries. So it turns out all the points that are on the boundaries, decision boundaries, that is the hyperplane we have, they completely determine the solution. We don't need points that are far away here or here. All these points on the boundary, these are support vectors. Now, I'll leave it up to you. You go and verify, because you do have the correspondences between slack variables and those points. Maybe you can plot it with different colors, something like that. I haven't done it, so that might be a good practice for you to just dig into it. So support vector means those are very dominant points on the boundary, and the decision comes from them. If the point is far away, it's not a support vector. The constraint is just inactive. It's easily satisfied. And the solver, now I didn't implement the solver, and I'm guessing the solver is just ignoring that constraint. Well, it's satisfied easily. So let's just focus on those that are hard to satisfy. It's focusing on those because that they determine the optimal solution. So although 103 variables, but it's a sparse model. Sparse means a lot of these slack variables are 0. I am not doing something smart here in the following, because I'm still using, I think here it doesn't matter. Later, when we use it on a linear basis, you can only use those bases that the slack variable is non-zero. You can throw away the rest of them. You end up with a much, much more compact model. It's so much easier to store, so much easier to recall for a new input. So anyway, there's a lot to say here, but we leave it for people in the machine learning course and later. But you already know, you know too much. You will bother your lecturer when you take a machine learning course. All right, so this is a line with a slack variable, and you see, we figured the boundary. It's not perfect, but it seems correct. It's something that is useful. Now, if you, for example, you can do it by hand, but when you use a library, there are tools to evaluate the performance, accuracy, precision of the classifier. And then this is not going to be 100%, maybe 95%, 90%, something that is high, but it's not perfect. But anyway, we fixed the problem. This was not solvable using hard constraints. I'm going to open the Gaussian version, and I run it before just to make sure. Very quickly. Non-linear classifier. I'm gonna, what am I doing? This is really when you see the power of the algorithm. I'm gonna add a photo for you here. That's how you should feel about it. Is very cute, but very powerful. So the trick is What if I had my model to be how about I introduce a feature map which you've seen before, maps X into a feature space. Specifically here is radial basis function that you've seen before, and this is the length scale. Now we're going to use each input to map it to a feature space. A consequence of that is that for each data point we have a mapped feature. Our function is going to be not a weighted sum of input, but weighted sum of those mapped features. So we're going to blow up the dimension of the function. We're going to have y equals, I call it j. And I changed different name, but you could use w still just to emphasize. J. And I use C here to emphasize that XC is the center. So phi j is really x minus xj. All right, so I'm using a Gaussian basis. You could use other things. There are many options. This is part of model selection. Okay, now the actual conversion of that classifier, it's a very tricky process. You should learn it into an optimization course in machine learning. But we're going to do a dirty trick to just make it nonlinear without too much problem. Now, my weights are now, if I have n data points, n data points, I will have alpha will be n plus 1. So now m, instead of being 3, is n plus 1. So m equals n plus 1. For every data point, I have a weight. This is a much more complicated model, instead of just a simple plane with 3 numbers. And for doing that, I am just going to go to the code. I do not change I'm just changing my basis. Instead of x, I'm using the feature, right? And I wrote alpha, but you can, I'm using here w. Don't get confused, this is the same as alpha. So now, w is n plus 1 dimensional. So so I didn't change anything else. I just changed my basis and increased the number of weights. So I'm using a more complicated model. And the reason I'm doing that, because I want to solve a crazy problem that no way you can draw a line and separate them. And I'm going to reuse code from your project too. I actually copied from there. I'm using RBF function. I'm using calculate v row. Then I'm building my regressor matrix. So I copied code from the project. You should be able to do it. So I'm going to separate the circle in the middle from the outside. This is not a hyperplane in this usual linear sense that we had. And let's see what we get. You see here, it's not much change. Instead of x, I'm building phi using the regressor matrix. And again, go through it. Let me know what you think. It's important you walk through it yourself. We are solving for (401) variables. This is already a high-dimensional problem. And imagine if it's a much bigger problem. You can have thousands, millions of variables. This is large data already. Now I'm going to create, look at this part, it's changed. I'm creating a grid over the region I know, then I query those points from my function, and then to know the value at the test point or query point. Then I plot my points, and I built a function using nonlinear basis, and then I'm plotting the contour plot on the data points. The top view, the contour plot. Remember, the contour plot was a plot that every line curve that you see here that is connected, the function has the same value. That's called a decision boundary. If I pick, for example, this line here, one of these, and I stick to that, I can threshold my surface using this function, and I say anything inside is class 1, anything outside is class 2. So that's really beautiful. We can, hard to imagine how we could do anything like this with, without that trick. And because the classifier is actually, the output is sine of it, I'm also taking the sine of it, but in practice, we should do something a little better. But if we just take the sine of the output, you see that one side is +1, the other side is -1. And it's a circle. It's not even a circle. It's a crazy curve on the plane. So this is our nonlinear classifier or support vector machine, SVM.